Hello friends, today we'll continue with multiple point loads. For that we need to calculate absolute maximum bending moment. So maximum bending moment is the maximum bending moment occurring at any section of the required beam. So for that the steps are as follows. First, calculate the resultant R of the series of the loads given. So R is given by summation of all the loads. R, suppose there are 3 loads, R is equal to W1 plus W2 plus W3. If there are 4 loads, add W4. So that is the resultant R. Now next step is step 2, location of X bar. So X bar is the location where resultant R is acting. First, let me consider the loads W1, W2, W3 and W4. So these are the series of the loads. For that we have to consider a section. Let these be 4 loads W1, W2, W3 and W4. I will write the distances. Before writing the distances, let me consider reference plane. So this line is the reference line. So I am going to calculate X bar with respect to this reference line. For this load W2, let that distance be X2 from this point. For W3, let that distance be X3 from this reference line. Similarly, X4 for this reference line. Now, X bar is given by W1 plus W1 X1. For this load, X1 is 0 because reference line coincides with this. W1 plus X1, W2 plus X2, W3 plus X3, W4 plus X4 divided by W1 plus W2 plus W3 plus W4. This is how you calculate X bar. Once you calculate X bar, mark that. So that is the location where resultant R is acting. This is an imaginary resultant. Now next step is selection of loads. So for selection of loads, observe the loads adjacent to R. Suppose here is the resultant. I have to observe this load and this load. Now how to select the load? So here two cases are there. If the magnitude of load are same, select the load which is nearer to R. Suppose W2 and W3 both loads have same values. If loads are same values, find out this distance and this distance. So whichever load is nearer to R, select that load. Second case, if the magnitude are different, means loads are different, select the heavier load. Suppose this is the resultant R, W2, W3. Suppose the resultant is here. So select the load which is heavier if loads are different. If loads are same, select the nearer load. If loads are different, select the heavier load. Next step 4th is arrangement of loads. The selected load and resultant R should be equidistant, means same distance from mid-span. Next, 5th step, draw the ILD for the bending moment for the selected load. We will take up a numerical example and understand these steps. So this is the problem which we have solved earlier. For that we are going to calculate absolute maximum bending moment. So these are 4 loads. This is the beam. X is equal to 8, L minus X is equal to 17. So I have to calculate loads at distance X is equal to 8 meters. For that already I have calculated RA and RB 444 minus 4. Shear force at section X is equal to 8. Maximum negative shear force 106. Maximum positive shear force 281. So absolute maximum means irrespective of sign. Absolute maximum shear force is 281.2. Now maximum bending moment at required section X is equal to 8, 2416 kilonewtons. So next step, calculation of absolute maximum bending moment. So under that step 1, resultant R. So resultant R is summation of all the loads, 120 plus 150 plus 160 plus 80, 510 kilonewtons. Now draw a small diagram. Show W1, W2, W3, W4. Mark the distance. So this is my reference line. Now for weight W2, distance is eg2. For weight W3, distance is eg3. Weight W4, distance is eg4. Now x bar is W1 x1, W2 x2 plus W3 x3 plus W4 x4 divided by W1 plus W2 plus W3 plus W4. Now W1 load 80 into 0, because this reference plane coincides with 80. 80 into 0 plus 160 into 2. These distances are already given. So these distances are 2, 2 and 2. So W2 160 into 2 plus W3 150 into 4 plus 120 into 6. So write those values. 80 into 0 plus 160 into 2 plus 150 into 4 plus 120 into 6 divided by W1 plus W2 plus W3 plus W4. So you get the value x bar is equal to 3.21 meters. Now draw a diagram. Show these loads. Show resultant R 2, and again these distances are 2 meters. This is also 2. And this distance is also 2. Show resultant R. So resultant R is at distance 3.21 meters from this reference plane. This is 2. So this remaining is 1.21 meters. So this is the arrangement. Step 3. I have to select the loads. Now this is the resultant R. What the theory says is observe the loads adjacent to R. This is the resultant. Observe left and right, 160 and 150. So observe these two loads. Now if loads are different, select the load which is heavier. So compare 160 and 150. 160 is heavier, hence mark this load 160 kilonewtons. So 160 is my selected load. Next step 4, arrangement of loads. The selected load, so 160 is the selected load, and resultant R are at equidistant from midspan or from the center. Now I have to place loads, this combination of loads, in such a way that my selected load 160 and resultant R, they are at equal distance from midspan. Say midspan is 0. Midspan means center. Now already I know distance between 160 and R is 1.21. Distance between 160 and R is 1.21. Equidistance means half. 1.21 divided by 2, 0.605. Similarly, calculate the distance between R and 150. So already I know from here till resultant R is 3.21, and from here 80 to 150 is 4. 4 minus 3.21, 0.79. Now I have to place this loading system in such a way that 160 kilonewtons and resultant R are at same distance from center. So 1.21 divided by 2, 0.605. So distance between 160 and center is 0.605. Distance between center and resultant R is 0.605. This is the arrangement of loads. Next step, I have to draw influence line diagram for 160 kilonewtons. So 160 kilonewtons, this distance becomes x. So already I know from this center to this edge is 12.5. So 12.5 minus 0.605. 11.89. Next, from center to this end it is 12.5. 12.5 plus 0.605. So you have the answer 13.105. So I will mark that distance here. 12.5 plus 0.605. So you have the answer 13.105. Now simply draw the influence line diagram for 160 kilonewtons. So already I know 2 meters, 2 meters, 2 meters. This distance from here to 80 kilonewtons is 11.89. 11.89 from here. Then from this 160 kilonewtons load till here is 13.105. So this distance is 11.895 minus 2. Now 13.105 from this end till here. Now mark the values. This value is x, L minus x by L. So this distance becomes x and this distance is L minus x. X into L minus x divided by L. I get the value 6.23. Now mark the ordinates for 80 kilonewtons, 150 and 120. Let these ordinates be y1, y2 and y3. So absolute maximum bending moment is given by 80 into y1, 160 into 6.23, 150 into y2, 120 into y3. Now based on same triangles, calculate y1, y2, y3. So y1 divided by 9.895 is equal to 6.23 divided by 11.895. So I have these equations. Y1 is 5.182. So similarly y2 and y3. Then absolute maximum bending moment is given by 80 into y1, 160 into 6.23, 150 into y2, 120 into y3. Substituting all the values, I have the answer. Absolute maximum bending moment is equal to 2722.57 kilonewtons. This is the absolute maximum bending moment. Absolute maximum bending moment means maximum bending moment at any section. Thank you.